Hello everyone and welcome to this introductory lecture on advanced geodynamics, theory and modeling. First, I would like to start the lecture with the question, what is geodynamic modeling? Geodynamic modeling is in fact the quantitative modeling of geodynamic and tectonic processes. You have here a very nice picture from Google Earth in which you see India-Asia surface nowadays. So India is right here. You see the front of the collision here. You see the biggest plateau right there. This plateau is limited by thrust faults and also strike slip faults. And you have this very impressive morphological feature. And of course, we want to understand what is happening inside the Earth in the lithosphere and below. And for this, we can use quantitative modeling. There are different types of quantitative modeling. And first, I would like to mention analog modeling. And what is analog modeling? So, analog modeling consists in first finding materials which will behave in an analog manner as rocks, but on a shorter time and a smaller scale. And then, once we have materials which are analog to rocks, we can construct a small size model and do a deformation experiment in the laboratory. So let's make an example. We have silicon. Silicon, you know, it's a viscous material, but you can deform it with your hand. Rocks, ductile rocks from the lower crust, they also behave viscous. On the very long term, you would never be able to deform it with your hand. But silicon and ductile rocks show an analog behavior. They are both ductile. The sand, on the other hand, it's an analog to the brittle rocks, to the brittle crust, because it allows to form shear bands. So it's a frictional material that forms shear bands, which will be analog to faults. Having silicon and sand, you can construct a small-scale model. This is an example of a collision indentation model. You see two colors of silicon. So this is silicon and this is silicon, two different silicones here. The top layer here, this is sand with a black marker horizon inside, and you see an indenter here. So this whole system is being pushed. There is a rigid block in there. And you see, for example, here, extrusion of lower crust on top of an indenter. This is an analog model. If we go back to the context of India-Asia collision, there has been a very important modeling work that was done in 1982, and you see here an image of an experiment. So this layered material here is plasticine, and here there's an indenter which has a limited width. And with time, it's pushed inside the plasticine, and it's forming a lot of faults, like strike slip faults, and also extrusion, lateral extrusion of the material, which has then been compared to the surface kinematics of the India-Asia collision. So that's for analog modeling. A second type of modeling is analytical modeling. What does analytical modeling consist of? First, you need to physically define a process. So this means basically we need to have equations, and we are going to solve for these equations. We solve for the variable of interest from the equation here. Let's give an example. You may remember from previous lectures, radioactive decay. So we have one ordinary differential equation here, dN dt, so that's the quantity of a radionuclide, is equal to minus lambda n, where this is a decay constant. This equation you can solve to obtain n. This is now an exact solution of this physical model. This is an analytical model that predicts the quantity n as a function of time. Analytical models have also been applied to study India-Asia collision. This is here an example where a solution to the Stokes equations, we will come back to this later in the lecture, has been derived in order to predict the flow of the lower crust below the plateau. So we have a topography here. You have a plate, rigid plate below, and you have a ductile horizon here, and you have a pressure gradient due to the topography, and the flow is activated in the lower crust. So that's one analytical model. A third type of model is the numerical model. What does a numerical model consist of? It's actually very close to the analytical model we were discussing before. First, we need to physically define a process. The difference here is that we are going to look for a solution, but numerically, we are going to find an approximation, good approximation, of the mathematical solution of the problem. So, once again, example of the radioactive decay, d and dt equal minus lambda n. The difference here is that we can solve this also numerically. There is not a big benefit for such a type of equation, but here is a numerical solution using a forward Euler scheme, which we have done in preceding lectures. This is now an approximated solution. There is a numerical parameter in there, delta t, which is the time resolution. Numerical models have been extensively used to study the India-Asia collision, and this is one of the important work that shows a collision model applied to India-Asia. So you see here a thin crust and a thick crust. So this would be the Indian side, and this would be the Eurasian side. So here you have a plateau with a denudation front. This is the upper crust, and this would rather be a middle to lower crust. And you see a lot of deformation is happening. And from this, you can also predict the temperature field. So you see the temperature isolines, these are isotherms, are, for example, bended upward towards the surface in this region here. So you have flow of the lower crust and upward bending of the isotherms. You can also predict the distribution of radioactive sources. You could predict the velocity field and everything, a lot of quantity of interest here. This is a complex numerical model, and for this you cannot derive an analytic model very easily, so it's easier to solve everything numerically. So that's for the numerical modeling. So one thing which is important to realize is that we get a lot of surface observation from geology. So if we still look at the India-Asia collision, this is a nice sketch here that shows you a reconstruction 50 million years ago, so before India collided with Eurasia. You see the position of an early front here, of subduction if you want, and the coloring of different terrains. So this information can be reconstructed from the geology. We have an idea of how to reconstruct in past the position of the plates and the location of the different geological terrains. A second very important player is geophysics, because with geophysics, and here in particular seismology, we can probe the internal structure of the Earth. And this is done with measurements made nowadays, so they will reflect the depth information at present day. So here you see a section, that's the present day configuration. You have India, and here is Tibet. And this is a section here through a tomographic model. So this is a seismological processing. And you see the continent in blue here, and potentially the presence of slabs at depths below the Indian continent. So this gives you a static information of what is happening nowadays at depth. Now comes the numerical model. The geodynamic numerical model can be used to combine both information from the surface kinematics to the present day information of the structure of the Earth at depths. And you see an example here of a simulation that includes the subduction process and the collision with two plates here. You see the vectors, they show the indication of how the mantle is flowing in response to subduction and collision of plates. What is nice with geological and geophysical observation and models is that one can derive data-driven geodynamic hypotheses. Here I'm going to take an example which I like very much. It's a conceptual model which was proposed back in 1991 to explain how the Norwegian Caledonites have evolved with time. So these are events that took part more than 400 million years ago, and this reconstruction, this is a 2D section here, is based on the collection of lots of data that could be made mostly at the surface of the Earth. So you see, in this section, you basically see a subduction going on, bringing continental crust from Baltica below Laurentia, and you see different suture zones. So this may explain the formation of high pressure rocks that you can observe in Norway, for example. And then to explain the rebound of the plate and the exhumation of the rocks, it was proposed by geologists that the slab would detach, would fall under its own weight, fall into the mantle, and that part of the slab would rebound, leading to an uplift. So that's a very interesting model where you have a plate that goes down, and then basically once it's losing the driving force for subduction, it's bouncing back. And this is something we did in 2012, where we actually ran a numerical model to test this hypothesis. So you have two continents coming close to each other. You have a subduction zone here. In a few million years, there's going to be a collision between these two plates. You see that this oceanic subduction is getting steeper and steeper. Continental subduction takes place, and then suddenly the slab will start to neck. You see deformation of the plate. It's losing the weight, and you get the rebound of the system and the exhumation of the high pressure rocks. So this is something that could be also obtained in a physical model. So the geodynamic model here is useful to check the physical viability of a conceptual geodynamic scenario. So that's one of the things that one can do with geodynamic modeling. You can check this. Another type of activity that one can do with geodynamic modeling is also to quantify and predict some variable of interest. So here is a model of a rift. You see a crust which has been extended. So this is the crust. Here the basement is in orange color, and all the layered horizons here are the sedimentary cover. You see the mantle is being opened here, This is the result of a computation already. And in white, you have the isotherms. You see that the isotherms are pretty high here, and basically in some places you have the temperature in the sediments which is going very high. With the numerical model, you can predict and measure this temperature rise. So if you put a probe in your model, you can, for example, study over time how pre-rift sediments are being heated during the rifting. And then you can compare to what is observed in the geological record. So this model was applied to the Cretaceous Pyrenean rifting and was aiming at modeling this temperature rise. And this kind of shown again that the conceptual model that was used to explain the opening of the Cretaceous Pyrenean rift is physically viable. But more than this, we can also quantify these temperatures or whatever could be the pressure and other quantities. Another cool thing here is application to the outcrop deformation. So in this picture, you see two type of structures observed in rocks. You have a gneiss at the top, and in this gneiss, you see a shear zone. So it's an extensional shear zone. This is moving down, this part is moving up. And below you see the same type of shear zone, but developed in the limestone and calcite veins alternance. Both of these examples are layered and they show strain localization under extension. And we can also use geodynamic modeling tools to smaller scale, to outcrop scales. Here is an example of one of these models where we stretch the different, a model of different layers here, which have a different viscosity. So what happens if you stretch a model which has different layers of different viscosities? Then you will start developing pinch and swell instability in the multilayer. And this pinch and swell instability will start to connect and develop low angle extensional shear zones. So that can be compared to this type of features. So you see first the outer layer will neck, and then this necking will propagate inside the multi-layer. And so this gives a model for the formation of shear zones. This was a new thing. So here the geodynamic model could be used to explore the dynamic evolution in a geological process. And this mode of strain localization in multilayer was kind of the discovery of a new mechanism, because it was impossible at the time to do the same calculation with an analytical model. It would be too complex. So what are the ingredients of geodynamic models? In general, most geodynamic models, they have a minimum thermomechanical coupling. That's the minimum coupling level that is used for most models. It means that we need to take into account the energy conservation, the linear momentum conservation, the continuity equation, and we need closure relationships such as bulk rheology and deviatory rheology. All these equations, we will come back to them later in the course, but the point here is mostly to show you that the models can have a high level of complexity. Usually it's not linear, and these are all partial differential equations. So it involves computing and method development. But the nice thing about these equations is that we can apply them to the outcrop scale, but we apply the same equation to the subduction scale. And when we study the whole mantle convection, we actually use the same equation, and scientists studying the dynamics of exoplanets are also using the same equations. So it's a set of equations that can be applied to different scales. Now, for geodynamic models to be successful, we of course need a lot of data and collaboration across all the fields of earth sciences. So, for example, in this type of model, we need a lot of knowledge from the paleogeography, stratigraphy, and the metamorphic data, but we also need high-resolution geodynamic modeling computations. For this type of model, we need structural observation in rocks and also accurate mechanical solver to resolve these thin shear bands. When we're studying a continental collision, we of course rely on structural and petrological observations that are made in collision zone, as well as geophysical data. But we also need very powerful numerical modeling algorithms. So the core of geodynamic modeling relies on having scientific collaborations with earth scientists from all fields, but also advanced skills in numerical tools and the constant development of numerical tools. So geodynamic models, they can deliver information about the geodynamic viability of concepts that are derived from observations, either being geological or geophysical or geochemical observations. They can deliver information about the internal dynamics. They can be used to quantify processes and predict occurrence of events. They also can be used to discover new processes and study multiple scales. They rely on geological data, collaboration with earth scientists of all fields, technical development of codes, and the collaboration also with computational scientists. So what we will do in this course, and what I want to do is to give you some basic theory and knowledge of quantitative methods which are needed to construct analytical and numerical models. So we are going to use simple examples and practical exercises. The practical exercises, they will involve hand derivation on paper and also computer programming. Basically, in this lecture, we will learn more about all the equations that are behind the scenes of geodynamic models, and also about how to derive them and how to solve them. And we also learn more about what are these closure relationships, how is density computed, why is viscosity formulated in such a way in geodynamic models. Anyways, that's it for the introduction.